All right. And yeah, so we'll talk about time series today. So this is kind of our introduction to time series. So I think both you guys have gone through at least that section with it, section 31, I think when it introduces time series. Cool. And know that the project, this module project is basically based around time series. So basically the next two sections, this section, section 31, and section 32 will basically tie directly into that project. So kind of like know that a little bit. I will be upfront is that time series is not my expertise. I have not used it in like industry directly. And to be quite honest, not every data scientist will use time series in the way that we're going to talk about here. But I think it does give you kind of a more competitive advantage, being familiar with like the concepts of, not just what a time series is, but also like the next section we'll talk about modeling and saying, what that modeling looks like and everything. So yeah, that kind of gives you a little background of like what this is. Our project is going to be, we'll talk about it more tomorrow, but it'll be more focused on, what's it called? Like, it's not necessarily just pure modeling, just because takes a lot of power to like do modeling and all that stuff. It'll be kind of focused more on the visual, like between visualization and kind of at the end modeling, but we'll talk more about that tomorrow. Okay, so let me go ahead and share my screen, and that way you guys, we can go through some parts. The right screen, hopefully. There we go. Cool. Oh, good. My windows didn't get moved too badly today. All right. So awesome. All right. Just real quick on the repo. I've been trying. I don't know if you guys have. I don't know if I showed this yesterday, but in case I haven't, I kind of made the repo a little bit more easy to manage for this version too. So, oh, we're not on module 3. We're on module 4, aren't we? Wow, we're just flying right through this, aren't we? So module 4, right? So basically, I kind of put these together a little bit. I just recently separated out this intro into visualization in intro. I think it makes more sense to just kind of know if you have an older fork, make sure you do a sync with the fork. That way you get these notebooks up and ready. But it's the same material, just kind of ordered a different way. All right. So first things first is introducing a time series. So before anything, I'd love to import my little guys so we can do some stuff. So this is going to be a little bit of review since you guys have kind of gone through the material. So I'll kind of go through it relatively quickly. But if there's questions, feel free to kind of like ask questions and, I can clarify everything. All right. So really the reason why we call time series data time series is when it's important that we consider the time as like an important key focus of the data. So progression of time is an important aspect. So if you think back on when we did our first project, right, with the housing, that does have time data in it. But I would argue that it's not really a time series like data set. And that's because the main focus really wasn't the time itself. It really was the time was an aspect of like that data row. So when we say time series, we're just saying like there is some kind of like progression of time or something about that data set that really time is like the key factor. So some kind of brief examples, stock prices, classic example, basically like, it's really important to say what is the progression of time, for the stock price and what the future will hold, right? Temperature over the year, atmospheric changes over the course of the decades. There's a whole bunch of things, time series. I was talking to a data scientist in GoDaddy, so like sells domains and stuff like that. And they were kind of talking about how the way people search for domains on like their, I use like, oh, I want to buy, victor.com or something like that. And, you would search for a query and say, oh, like maybe I try this one instead, like victorg.org, and go forward. They considered that like a time series where basically the progression of going to each individual part was basically a time series, and they're kind of like the view of the model. So you can kind of see like if the progression of time is an important aspect, that's when we say it's really a time series. Okay, and there's a lot of things that can fall into that category. Okay, so kind of some basic stuff. This is kind of similar to curriculum. So I think it's going to be a mix between curriculum stuff and kind of like the little things I kind of add in here. So here's a CSV, and I've actually opened up the CSV. Let's go modeling, time series, and in CSV. You can just simply see it's a very simple CSV. We have the date here, represented right here, and just a value, so daily minimum. So I think it's the daily minimum temperature for that date. And you can see basically, or not this date, for the month. So you can probably guess is that in January 1st, 1981, the minimum temperature was 20.7, and for February 1st or February 1981, 17.9. So you get the idea. Like that's kind of this time series here. All right. So oops, didn't mean to do that. So let's go ahead and load it in, and you can see here basically we just read our CSV just like normal, and we run this. Cool. All right. basic basic data frame. But the thing is here is that, first of all, some issues with this, right? One is like, this is fine, right? 20.7. But this right here, this date, is definitely going to be looking like an object, right? It's going to be a string, and it's really not a string. We really want to say, hey, this is like encoding information of like order, right? So we want to make this more readable as like an actual like thing we can manipulate. And this is where we use something called a date time object. So we're going to make that column right there. Basically, that's just a string. Basically, the computer's like, I don't know what this is. Oh, I read this wrong too. You see? Good thing I looked at this now further. This is the 1st of January, 1981. So yeah, even more confusing. So for the record, always do year, month, day if possible. That's the only correct way to write the date. Anyway, that's beside the point of formats. But anyway, we can actually take this date right here and put it into a date time object. And what's really nice about this is that it'll allow us to manipulate based on time a lot easier. So we'll kind of see what this looks like. Because remember, this is just a string. So we'll take our date, and we're using pandas as toDateTime. So datetime, just know that datetime objects kind of exist beyond just even Python or pandas. They also exist like in JavaScript and stuff like this. So if you talk about a datetime object, it's going to be pretty universal. So the way we can convert this with this PD toDateTime is we take our column right here, and we have our arguments right here with arguments about our format. And so this format right here is pretty universal. So if you were, like I said, like switch over to like JavaScript or whatever kind of language, or even just Python in general, for the most part, we have the same kind of like criteria where we use like %d meaning the day, % meaning the month, and %y meaning the year. And so it knows to put this in. There's other more advanced stuff too you can do, for including like the week number, the week day, like there's all these different aspects you can put into here. But since this is just basically our day, month, year, we can put it like this. So basically let's look for this kind of format, which we can see is right here, and it will try to read it as a date time. And if we do this, then we can go ahead and convert that over. One last thing I put right here is that we're actually setting the date as that date column as the index. And so the reason why we do this is because it's really not, it doesn't really make sense to say, oh, this is the first data point, second data point. Like that's not really what we're counting. We're really saying the date is the most important aspect. So we want to index it by that, saying, hey, the date is really the main focus of this data. So it should be treated as the index. And we should have a unique date time too. So it should be all right. So that makes it nice and easy. And we can look at what this looks like. And you can see here is that we have our nice date time right here. Kind of, I'll put it in here. And you'll notice too, when you set an index that's not the default, which is just basically just counting, you'll see that the index basically will be pushed downwards. So this is how it visually shows you, hey, this is the index. So now basically this is kind of like how each row is identified. Okay. And let's see here. Yeah, cool. And you can see here, since we have our index here, you can see it's a date time index. So Pandas looks like, oh, and I see this is a special kind of format. So it's going to make it easier for us to like manipulate our time series. Cool so far? Sound pretty good? All right, easy stuff, right? But I think it's good to kind of walk through what that looks like. All right, so let's go to slicing our time series. So like I said, we made it really special where now we can actually slice through and kind of manipulate the the time series, basically a data frame, using kind of date in mind. So you notice here, if I did this with a normal kind of data set without doing the index and whatnot, or a string, this really wouldn't make sense, right? 1990 to onward. But since I know that, or basically the data frame knows that this is a date time kind of indexed file, I can just use the date directly in here. So I can say everything past 1990. And so if I look at this, for example, you can see here, sure enough, I get all these points. Cool. Okay. So basically you can use the date time now to actually manipulate the data a little bit easier versus like having to do something where you have to like put in the string and kind of match each date and time and everything like that. It makes it automatic. Okay. And I don't know why I showed this. Oh, I was just showing that it is in fact like a different part. Okay. So let's move on then to, so this is kind of a follow-up. Why should we make the date as the index? So kind of like a quick summary, right? Like, why do we make the date as the index? Like, what are the advantages?
You can do that handy slicing. And it also, you can use it when you're plotting. You can just make the index the x-axis values.
Exactly, yeah. So it makes it really easy. It basically looks for you don't have to like say, oh, it's data point 0, 1, 2 or whatever. It knows already to put it in order. So again, yeah, we're basically informing Pandas like, hey, this is the main focus of data. Really stick with this kind of information. So that's kind of like what we're seeing here. Cool. Cool. So it's good to kind of do a quick check. So some quick stuff before we talk about visualization itself. We can do something resampling. So this happens when, for example, you have two different sets of data sets or two different time series, and you want to combine them together to form one massive time series, right? Or like you want to take from two different sources, let's say like two different sensors or something, like let's say like weather data or something. You put it together and you say, okay, now I have the full weather data. Well, the thing is that depending on like how it collects it, for example, maybe you have weather data that is collected from one thing like every day, but another one's collected every month. And it'd be kind of useful to, you know, maybe like combine those together in some fashion. But they're not going to match up, right? So this is where downsampling and upsampling might make sense, where essentially we'll either upsample, basically create new data in the data that doesn't exist. So for example, if it's monthly data, we'll basically assume like, well, okay, this monthly data, we're going to make it daily, right? And then combine it together with daily. Or downsampling, where it's like, well, we really just want, you know, one value for the month. So we're going to basically make it so this time series that has every day, we'll just make it a monthly data. And so that we can combine it more easily. Okay, so this is a couple of strategies. And I put the little link here to the reference for Pandas DataFrame for resampling, which looks like most of the stuff is actually deprecated now. That's okay. But for that, anyway, basically just know there's kind of a way to resample with Pandas. And I'll kind of show you guys a little bit what this looks like. So downsampling, like I said, we're resampling at a lower rate as it's phrased. Basically, it's like, oh, you have information and you're going to condense it down into less information. So you will lose, you likely will lose information, right? Since there's stuff beyond just, what's it called? Like if you go from day to month, obviously you're gonna lose information. But it does make it more computationally efficient, meaning that you have less data to play with. Like maybe you don't need every single day or something like that. Maybe you need weekly data or whatnot. So it makes it a little bit more efficient. That's usually what we do with downsampling, is basically like, well, we have a huge amount of data. So imagine if you had a sensor that's collecting data every second. It's like, well, I don't need every second, right? I need maybe like at most a minute. And so we can basically reduce the size of our data. It makes it a little bit easier for us to make predictions off of it. So a quick example. As you can see here, we have our monthly, which is our DF temp. Oh, sorry. We have our DF temp, which we saw from earlier up here. Okay, so we can see basically it's done by every day, right? So we can resample this to make it monthly. So note that this resampling here, the same function I showed up from the documentation, and I'm just passing MS, meaning like monthly. So there's certain, you can look up, you know, in the documentation exactly what parameters to pass through here, but this, they know this is going to be the monthly means. So I can pass this in here, and I can basically make that monthly mean. And now I can actually see is that each day now, or sorry, not each day. Oh, this doesn't help. There we go. Okay, now we have the monthly mean. So you can see the monthly mean here is that now we have the date time. It still has to be a specific date. So it's going to say January 1st, February 1st, and so on. But you can see here, this is going to be the mean average here. So this might be more useful for us in combining the data points, or maybe it's more efficient for us. Like for example, if we're predicting like the temperatures, temperature per month, you know, in the future, right? We don't need every single day. Like that might be too much information for us to actually be useful. We can average together and say, okay, just per month to month to month. Okay, makes sense. Cool. All right, so I'll keep going on to upsampling then. So upsampling is kind of the opposite, right? We're resampling at a higher rate. So the idea here is that we actually, what's it called? Like, let's say, for example, you do something like a week, like measure something weekly or something like that, but you need it to be instead daily, right? Maybe you have information daily. It's like, well, then we'll go ahead and expand it out to weekly. Note that you're kind of extrapolating, right? Basically, you're kind of like increasing this out. You can also keep it null values, where essentially it's like, well, okay, let's just assume like Monday or Sunday or whatever your day, the first day of your week is for your data set. Say, okay, let me keep that day as like the week part, and we're just going to copy those parts in for every single day so we can combine the data more easily. Is it going to be super accurate? Maybe not, but at least it will allow you to combine the data together to make it more useful. So sampling, just kind of knows that the difference between here is that downsampling, you're losing information. Upsampling, you're keeping the same information, and you might even actually kind of give more information. Can always be aware of like when you would want to use upsampling versus downsampling, or just keep it the same. Okay. So example here, I have our data temp, for example, and I'm just going to resample for 12 hours. So that means instead of having everyday data, we're going to have it instead every 12 hours. So that way maybe you have a data sensor that's records it like at midnight and noon and has that temperature go through. So I'm going to create this by daily data. And you can see here now, instead of having just simply January 1st, we also have a time here. In this case, midnight, 12 p.m. and so on. In this case, you can see it actually by default will have null values. And this might make sense. This might be like, okay, cool. Like that's all we want to do. And then we can fill in this part with maybe extra data that we have. Maybe there's another sensor that was recording at midnight, and we can combine that into here. In other cases, for certain things, it might make sense to actually fill it out. So you can see we can just use .ffill, and this will fill out those blanks in there. So you can see now, instead, basically we have our average in here. So again, not all cases make sense to do one or the other. So you have to kind of consider what the context is. And you can see here in this case, I can even go in up to like 1 hour. So this one in this case will fill out for like a whole hour between, let's say January 1st, right? So all the way through. And you can see next one. Okay. Cool. All right. Any questions on that resampling? Okay. Yeah. And I'd say the most part is upsampling like this is usually useful when you already have some kind of formatted data, or like you've been building a model with like essentially like, let's say, or maybe not even a model, just like observing it for, what's it called? Like you've already had something that's in hourly data, and now you're like using it again for this data set, but you only have daily data. It's like, well, let's go ahead and make it happen so we can actually do something useful with what we already have versus rewriting the whole thing. Or if you want to combine data. Downsampling, for the most part, can be the same thing if you want to combine data or if you have something in a certain format, but it can also be useful just being like, hey, like this is a lot more information that I actually need. So it might make sense to kind of condense it down so then we can go from there. Awesome. So cool. Now that we got those parts, now the fun stuff, the visualization. So this is kind of like my little fun things. Hopefully you guys like pretty pictures too. So cool. So visualizing time series. So there's a whole bunch of ways you can visualize these things. So kind of talking about a few things is, let's hear it. Basically for time series, we really want to show changes over time, right? So again, the main focus is the fact that it is based on time, right? So right here, we'll take in the New York Stock Exchange. I think this came from the curriculum as well. And I think the month, the value is basically, so it looks like column name was the month. So I think it's monthly data. And then, oh, good, average monthly returns. So the returns from 1961 to 1966. Cool, from curriculum. Look at me. Past Victor is so nice to put this in here. All right, so we run this guy, and you can see now is that we got our nice monthly data over here with our date, time, index, and all, and you can see the monthly return. Ah, beautiful. So now we can check out a few things. So there's a few ways we can plot these things. So one thing we can do, a line plot. So line plot, it's probably what you typically would see for most time series, right? So you can kind of see like, for example, because it's a line plot, it implies that they're basically interconnected, which makes sense a lot for stock data. Note, not all data that is set in time makes sense to actually be connected from the previous time, right? But here in the case, like you expect that the previous, like let's say the previous price of a stock would be dependent on the previous one, on the day before. So it makes sense it kind of follows through. And that's really what a line plot is implying. So kind of be aware of that when you're going through. And note that too, because we made the date time, the index, right? It automatically knows, hey, I didn't have to put in this x-axis. It went ahead and just put this in here. If we hadn't done this, it wouldn't know what's the first data point. It would just basically, oh, whatever the first data point is in here. But if for some reason the CSV was out of order, it might not necessarily, won't necessarily reflect the fact that it's changing over time. It might just be data points that are out of order. So kind of be aware of this part. But sometimes this doesn't make as much sense, like I said. Sometimes like if you're saying like, I just want to see a distribution of points, a dot plot makes more sense. So in this case, I can do basically the same thing, but in this case, I use style with this guy right here. So more matplotlib kind of styling. And you run this guy, you can see we get a little dot plot here. And this might be useful to see the distribution of returns. So again, this is return. So maybe it might not make sense to actually look at the previous date and just want to see what's the distribution of this date. So a dot plot might be useful in this case. And so even though it is a time series information, maybe it's not completely dependent on the previous day. So in this case, a dot plot. But for the most part, if you're thinking about time series, it likely will be something along a line plot. Okay. Does that make sense to everyone? Cool. Any questions on either of these two parts, or one that's appropriate? All right. Pretty straightforward, I think. Now we get some kind of fun stuff. So like I said, when do you want to use a dot plot versus a line plot? Get the idea. So let's say it's like, okay, we have a lot of data, so 1961 to 1967. It's like, okay, we can see the overall trend, but what if we just wanted to see how it changed over like a particular year and see how those compare? So one thing we can do is grouping these plots together. So like I said, like we want to look year to year, for example, like temperature throughout the years. So you can imagine, for example, the temperature is going to, fluctuate throughout the year, right? And we don't want to just see like this overall trend going like from like, let's say 1900 to like 2000, right? Like that might be an important aspect, but you might want to just look at every individual year and see how the temperature changes throughout that year. So we can do a few things. So example of all separated annually. So what I'm doing here first is basically going to group them together with this grouper function. And what this does, this is from the curriculum, is basically doing a frequency of annual. So it's going to group them together. So it's like, okay, let's say like 1950, 1951, 1952, it's going to group those together. And then with those groups, I can actually go ahead and plot them against each other. So this is going to group it at first. And remember, since we're doing a group by, this group by is basically not going to give me anything. Like if I try to print out year groups, it will look the same as a data frame because I haven't done anything like, aggregating it together. But once I have that part, I can actually take each year here and actually plot out each individual point. So this groups.ravel right here, this ravel basically allows you to look at the data. It like basically like ravels it out and ready for us to use as a series. So I would definitely check out like Ravel in the data frame, kind of play around with it, get a feel for like what it's doing. But I think for the most part, you can kind of get the idea. It's like we take a year, we take the group, and this group right here basically is saying, that annual data. So if I do this now, this will basically make a plot for each year on a separate plot. So you can kind of see here the general like 1961, 62, 63, 64, 65, 66. I think this is, what is this data? Oh, it's New York Stock Exchange. Okay, so you can kind of see how it changes the returns over time. Now this is useful, right? Like you can kind of see a general trend here, you can kind of compare, but I don't know about you guys, what might be some issues, I guess, like with this, like at least a visualization, either trying for you to explain stuff to yourself or to others?
If I wanted to know like which of these years was different from the others, looking at them all split out like this makes it I have to be like, okay, well, this one went down and this one went down, but that one went up and this one went down. But if they were all overlying and one of them was different from the others, I'd be able to see that more easily.
Yeah, good. And I think that's kind of the biggest part. It's like you have to look at each individual colored line here by itself. And then there's another thing too, if you look carefully, the y-axis here, I mean, I could change this a little bit to make sure it's the same thing, but you can see here it's just like, oh, also like the y-axis isn't the same. So like if I wanted to compare how did 1961 to 1965 compare, I first of all have to look at this and then look at this one over here. And it's a little hard for me to kind of quickly go through here. And then if I'm not being careful, I might assume that's, oh, this went from really, like this started up really high and went low down here versus this one, stayed up pretty high. But if you look at this part, like, oh, this was already at 0.05 and the negative 0.05 here. So this one barely changed, for this one actually changed quite a lot. And so that might not be super obvious. In some cases, all you want to do is just to see how the change goes through. But other times you might actually want to compare these values directly, right? So especially if you want to compare them directly, so kind of overlapping, like Jenny had suggested, put them all together. That's exactly what we can do. So when we can do this, let's go ahead and run this down. We can do the same thing where we do, instead of subplots here, equals true. This is what a subplot is. So each plot's on top of each other. We do the same figure size. So this because I made it a little bit bigger. And then I'm going to go ahead and make the subplots here false. So that way it plots it all together. So if I do this now, you can see here, I get all of the plots together and you can see the scale is the same here. Now I can directly compare each one. Now, this might be better in the sense of like, okay, now I can actually see where they all started off. For example, for the most part, they all started at this level, but some started kind of on the lower end, right? And for the most part, it looks like they kind of ended, some started up over here and some people kind of went down here. And so it's a little bit better, but you can tell too, it's maybe not super clear, right? It's a little hard to like see exactly what's going on here. So there's other ways we can kind of show these show these other plots going forward. So we'll see a few other methods, but for the most part, line plots tend to be the most common things you'll see for time series because they're connected together. Okay. So I'll make sure, good. All right, so a distribution. So a couple things kind of sidestepping off to the side is that sometimes you might want to check out the distribution of like how, of like the data itself. So like not just essentially how it changes over time, but also just seeing, for example, does the distribution of the data actually like say uniform, checking for normality. So statistical testing. or if we want to do a first check on like raw data and transform data. So like it's a quick thing for us to see like, is this data distributed evenly and such. So we can get a little bit of a pattern before we look into like how the progression of time comes into play. So classic one is histogram. So in this case, we're basically completely ignoring the time data itself and just seeing what the values are. So you can see here in this case, I can see the values going forward, and then you can see it change the bin size. So you can see this is stuff you've probably already seen before. Like we know how to make histograms, but no, you can still do this with time series to see like the normality. And you can see it's pretty normal, at least the returns. You know, it might be a little bit like some extra part depending how I bin it, but it's relatively normal-ish, right? Another part we can do is density. So our density basically, it's kind of like our histogram here, but our KDE. So we've seen this before too. And you know, you can see, like I said, it looks roughly normal. So I prefer KDEs over histograms for the most part, just because it gives me a more, you know, organic looking shape. I get a better feel for it. That's just my opinion, but you can see there's that difference going on top here. Okay, so another distribution plot we can have is a box plot. So what's kind of cool is that we can actually show the distribution over time. So we can actually see things like, you know, find outliers within that trend or seasonal trends. And we can kind of check out what this looks like with an annual box plot. So you can see here, this is basically the different values over time. So we can actually see the distribution for each year, and then we can actually see that distribution change over time as well. So I think I like this one a lot because a lot of times this will kind of show you a little bit like, you know, within this 1 year, 1961 had a lot of fluctuation within that part, right? And we can kind of see is that 1965 for the most part stayed relatively small, like, you know, that the distribution kind of stayed within itself. So it was kind of a pretty like, what's it called? Not a huge difference in returns throughout that year. But we can also see an overall pattern too. It's like, obviously this is a box plot, so we have to consider that it's not just simply going, you know, from beginning to, it's not going from like this value to this value. It's kind of going, you know, within here, and then the next year going within here. But you can see if you just kind of summarize it all together for, if I took like just all the averages, right, for these different years and then just plot this part, we just connect these points together and you can kind of see the general flow through here. So I think it's a good compromise of like saying, oh, what's the distribution within here this year? And then also seeing what the flow of the information looks like as it goes over time. Okay, so it's kind of a good compromise, I think, between doing something like this where we're seeing just a distribution, like if we did this for just 1 year, and doing a line plot for every single part. Okay, cool. Any questions on any of these plots so far and how they might be used or useful? Okay, cool. So last one I really prefer is using like a heat map. So a heat map, I think it shows a really great way of like, it's not great for every kind of data, but I think it's also a great way to kind of like combine this information together. So I'll kind of show you a little bit like how this could be useful. So in this case, I'm going to go ahead and plot out, oops, I do not have DF temp. What am I missing? DF temp, I had that right. Oh, I know why. I split this up. Sorry, everyone. Let's go ahead and read in this point. This is what happens when I change things right before the study group. Okay, and let's go through a little bit then. Yeah, I'll just copy this over. So this will put it back into a time series, right? So I'm reading the data right here. I'm creating our, making it into a date time, and then just setting the index here, right? So there we go. Okay, and let's see here. We'll make sure this, okay, so I'm gonna have my temp annual, I'm gonna have a new data frame, and I can go ahead and take the date temp here, and I have this nice, beautiful data set. So let's just kind of check this out, just to, so cool. I basically put this in format, so now you can see it grouped together. So you can see here, each column now is each year, right? And each value basically is represented on these parts. So you can see like, you know, the first month, the second month, the third month. And this makes it a little bit easier for us to plot it together. That's what this grouper and raffle is doing for us. Okay, so the first thing we can do is try to do the subplot like we did before. Now, if I do this guy though, you will see that is really awful to look at. Like, I don't know about you all, but like, I can't really tell exactly what's going on between the different years. Like I can kind of look at between 1981 and 1982. The scale's a little bit off, which I could change, but even looking at just like assuming the scale's the same, it's a little hard to see exactly what's going on. And then if I want to compare 1981 with like 1990, I mean, I don't know about you, but like I just cannot like visually like pull this information all together. So we saw before, we can probably put them all together in one plot, right? So if we put them all together in one plot, we can see this beautiful mess, right? So this is kind of nice because now this definitely does give us a little more of a pattern. It's like, oh, we can see throughout the year, it starts off at a certain temperature and it kind of goes down, you know, towards here, towards like, you know, looks like the middle of the year. So maybe it's like the Southern Hemisphere or something like that. But we can see it kind of go down and then come back up. And so we see a general pattern. But if there's any point where I want to see each individual date or each individual like year, there's like no chance in hell, right, that I can actually pull out any information from any individual year. So I made a kind of compromise, like, well, I can't see every single individual year, but now I can't see them all together. And now I have all this stuff together, but not any, I can't pull out every individual year. So to kind of combine this, I think a great solution is using a heat map. So what we can do instead is take the same information here and basically plot this in a heat map itself. And so when I do this guy, this is what I love. Oh, look at that beautiful just visualization right here. So what's happening here is that each each horizontal line, which you can kind of visualize right here, is 1 year. So we can actually use this one line right here to see what the progression of the temperature is. So we can actually see each individual year relatively, you know, easily compared to this thing over here. But at the same time, we also see it grouped together at the same time. We see the change over time from the left to the right over here. And you can also see, in this case, this is kind of blue and this is red, which kind of makes a little more sense for temperature as well, like a higher temperature and a lower temperature. You could probably adjust these colors and stuff like that for your audience, but at least for a quick exploration data, assuming you're not colorblind, it's probably a good kind of like initial kind of look forward. Okay. So yeah, anyway, I think this graph right here just makes me want to cry. Like, it's so beautiful. But yeah, so you can see there's a whole bunch of ways you can visualize this stuff, and it just really depends on like what you're trying to see. If I wanted to see just a general trend, I can just plot these all together and see how they generally go through. If I really want like individual like plots, I might either do something where I look at just 1 year, or I might even do something like this where I see the general trend. But if I want to see them all together, this is actually, I think, a great compromise of like, be able to combine them together and still go through. One disadvantage of this, well, let me ask you all, what's one disadvantage of this compared to maybe one of these two plots? And I'm thinking, to give you kind of a leading kind of part, is I'm thinking about the values of like the actual years. Can we pull information from the value information from this graph by itself? Not really, right? Like what value is this year right here? It's red. Like, you can't get any direct information here, but this might show you more of the pattern itself versus the maybe I don't really care too much for this exploration, like what the exact number is. We just really care about, you know, what's the general like trend going on through here. So yeah, cool. All right. Any questions on any of these visualizations, or like how they're useful or how they might be used? All right, cool. Yeah. So again, visualizations is just like another way for you to present the same information, right? I like to say like our visualizations just really depend on the context. It's just a better way. It's an easier way for us to process that information versus looking at a bunch of numbers and stuff like that. Okay. So let's move on to trends. All right. So let me minimize this guy. Are you minimized? You're not minimized. You lied to me, Eros. Okay, so all right. So now we're going to go into a little bit of like looking at a specific trend. So like we kind of saw some visualizations, we saw about some intro and stuff like this, and we're kind of moving more into section 32. Okay, I want to make sure I got this right. Yeah, so we're going to go more into that section 32, which is going to be kind of like the modeling. But since there's all these different parts, it makes sense for us to go into it now. Okay, so let's go ahead and start this guy up. So right now I'm just going to read in our data, our New York State or Stock Exchange monthly data, right? So I'm just kind of pulling this together. And in this case, what did I have? Oh, it hasn't generated data. So this is just, I think this is from the curriculum. And so this is probably like something very similar where I just basically creating some data in here so I can make a time series. Okay, so just kind of know, got our time series all loaded. Now we can talk about different types of trends. So we have our different types of trends. We have, like we said, in here, stationary, linear, exponential, periodic. So a basic trend, or a trend really is just saying like, how does the data evolve forward? And so the first kind of like trend that we have is basically no trend. Essentially, like there is like nothing changes. And so if we look at like what a stationary trend looks like, and I realized too, my images are missing. Where did my images go? Okay, I'm going to show you from this blog since I like this blog's visualization. And this looks probably very similar to the curriculum's visuals. Here you go. So this is basically our stationary series. And so a stationary series basically has, essentially it's stationary in the sense that it is not changing over time. So you can see here, for example, like in this red here, the bad, not stationary series is this is an upward trend, right? We're changing over time in value. So the mean of the series is moving up versus like this one, technically, it's quote unquote not stationary, but it's like basically staying in the same spot. It's basically fluctuating along the one point. The next part is saying our variance doesn't change. So basically saying that like we really have like a homoscedastic, view. Like the change, like we don't have, what's it called? It doesn't balloon up and then balloon down or balloon upwards, like in kind of like the trumpet kind of fashion where the swings get larger and larger as we go further in time. Compared to this one right here, you can see like it does kind of increase over time. In this case, it looks like it kind of decreases down, but it could keep increasing, for example, and that would also not be a stationary trend. So for the most part, like our values don't really fluctuate too far up and down, okay? And then last part is our covariance. So our covariance here, think of like, I'm trying to think of it, like how it varies amongst itself. So this one's kind of varying over time, but this covariance is basically saying, like the fluctuations change in spacing. So you can kind of see here, like, everything's kind of evenly spaced, but this would be a non-stationary in the covariance, like a non-constant covariance, because what happens is the seasonality basically gets more frequent over time. So in this case, we can see like it starts off, spaced out, and then it gets really frequent over here. And that basically is saying, like, basically, if you think of it like, if you, how do I say this? I'm trying to think of like a good phrase to say this, but if I were to split up this series like this, you can quickly like know that this is going to look very similar to the previous one. It's correlated with itself, right? That's kind of like the covariance is really saying. It's like it's correlated to itself. But this one right here, if I look at it, like a split right here and a split right here, like first, this is a different kind of size, and I can't really look at the previous one and predict what this is going to look like. Basically, that spacing between the two is changing over time. So you kind of have three different aspects. This is usually, these two are usually the ones that you're most commonly like, or like most obvious, like, oh, these are not stationary. This one's a little more subtle because it basically implies that there is some kind of like seasonality, basically period. I shouldn't say seasonality since we haven't talked about it, but like basically how it fluctuates through time, or not, like oscillation. There we go. That's the word I'm looking for. It's oscillating, right? Well, this is oscillating at a different frequency, essentially. So kind of an interesting one. But if any of these are in here, it's not stationary. So ideally, the reason why we want stationary trends like this is so we can actually do some analysis. It basically removes a lot of like the extra factors that would come in from modeling. So if we have something that's more stationary, we kind of already know like the only thing that's changing is over time. So it's like, oh, if we have a stationary trend, we know, let's say this is like January and then it happens again in January, we know what the approximate price would be, if it was like price of like a shoe or something like that, that changes over time. Cool. Does that make sense to everyone? Cool. All right. So back to my notebook. Oh, wait, let me clear this guy. There we go. Back to the notebook. All right, so we can see here is that we have our New York Stock Exchange returns for the month. And you can see for the most part, like it's relatively stationary. Like, and this is where I'm saying there's no direct pattern that we can tell exactly from this. Like if we look at the long term, it doesn't seem like there seems to be like a difference in spacing, like maybe parts of it. So obviously we're never gonna have a perfectly like nice theoretical trend going up and down like that. But for the most part, I would say this probably looks pretty stationary. And we'll talk about like how we can actually assess this thing. Is it actually quote unquote stationary? But believe me, at least for now, right? Cool. So next part's a linear trend, which is basically what we saw in that first image. There you go. Is our upward trend like this. So pretty simple, right? Basically, over time, the average, like if I look at between 1963 and 1964, that average is continuing upward. Okay, so so much of that is a downward trend. Okay, so cool. We know the difference between up and down. Simple enough, right? Okay, so an exponential trend is going to be a little bit different. It can go downward as well, but usually we talk about exponential trends going upward. And note that basically this is more like a linear trend, right? We can kind of see a line kind of drawn through here going upwards or downwards. And an exponential trend is kind of interesting. Let's say it's an upward, what's upward trend? Upward exponential trend. And so what's interesting, you can kind of see is that it kind of goes up and then it kind of boosts up faster and faster and faster. And that's a key point of exponential. But one thing I do want to note to you guys is that if you look at the very beginning part right here, this one just looks like kind of like a relatively simple upward trend. Like if I tried drawing a line through here, let's see if I draw a line here. There we go. You can see at first, like if I drew a line, for the most part, it looks like an upward trend, right? Like, you know, like it's a little hard to tell like if it's not. But then once it gets over here, you can see it kind of comes up. And I can try to draw an upward trend here, but then you can see here, oh, upward trend go kind of messes up again. So that's a key part of exponential trends is that at the beginning of the exponential trend, it tends to look like a linear trend, but then it will eventually kind of ramp up faster and faster and faster. And that's the key marker here. So note that this kind of happens a lot with prediction where like you might start off with a nice, you know, upward trend, which is relatively simple, just a straight line. And you might say, oh, wait, like as you kind of go through, it actually turns out to be exponential and then it increases further and further and further. So something to kind of keep in mind as you kind of look at different trends. Okay. So, and then our last one that is not stationary is our periodic trend. So this is the oscillation going forward. So one, we have these like big spikes over here, but you can even see overall in this average between this noise, you can see kind of like going up and down, up and down, up and down. Okay. So this is kind of having a periodicity, or we can call seasonality. So the seasonality basically meaning that there is some kind of like quote unquote season to it. This could be over, you know, a month, over a year, could be over minutes, you know, kind of thing. The idea here is that we have some kind of pattern. And here you can see that this one's pretty, you know, let's see, if we got rid of the seasonality, it would be pretty flat. But you can see because, that all it has is that periodicity going here. But here you can see that it's kind of periodic and then it kind of goes up right here. So now that you can have a trend that's kind of combined together. So we can see there's also a periodicity, but also it kind of increases over time. So an upward trend. Okay, so that's really like the main trends that we're gonna like kind of like notice and kind of look for. And so we can do things like assessing these trends and saying, okay, like what kind of trends are in here? So if we took some data here, in this case, this is the, what data is this? Oh, this is the random data I made, or not the random data, but the data that was pulled up from, here we go, from this guy right here. So we got this data here, and now we're saying, okay, like look at this kind of trend going forward. And I think this actually comes from the New York Stock Exchange data. Maybe that's the same one. Anyway, so we can kind of pull this forward. And so we're like, okay, let's go ahead and start assessing these trends and see if we can kind of like explain it. And the way I kind of explain this is that we're trying to get it down to a stationary trend. And the reason why is because we're really trying to like remove this extra information that we can explain. If we can explain an upward, like if we know we can just say, oh, the trend's basically going in an upward direction, then we can get left with just basically the little fluctuations. So that's kind of what we're trying to go towards, is trying to get, can we get to a stationary trend? Okay. So a few things you can kind of do to help kind of like average things out is something called rolling statistics. So the idea here is we take the average of the number of the past data points over a time period. So the way I kind of like to explain this is like, we're going to take a little window and say, what's the average within this window? So if you imagine, I wish I could kind of drag these things easily with Zoom's drawing tool, but that's okay. If I had something like this, we're going to average all these together and say, okay, that data point, let's say it's like average is like right here. And then we move the window over a little bit. I'm going to make it more dramatic. We move the window over here, and we take the average of just in this window now. Say, okay, the average is like right here. And those are the points that we're going to plot. So basically we're averaging it over. So that's why it's rolling statistics. It's like, imagine rolling like a window cart, like going across, going all the way through, and we're averaging over those points as we roll it through, right? So I think it's best if we kind of see what this looks like. So in this case, I'm going to do a rolling mean, but I'm also going to do the rolling standard deviation. So now that basically I'm going to take this window, in this case, I'm going to take in here 6 points, and I'm actually going to change this to 6 as well. And I'm going to basically move that window so it looks at the previous 6 points to find the mean and the standard deviation. So if I do this now, you can see here in the red, so the blue is the original trend, right? You see that exponential trend. And right here, we can see the time series now being averaged over. I'm averaging over the 6 previous points and plot that point. And then moving to the next point, 6 previous points, plot that point, and going forward and basically averaging all the way through. And you can see here the standard deviation as well, like seeing how that changes. If I wanted to look at just the standard deviation without being averaged over and stuff like that, let's see here. Wait, I'm a little confused by that. Okay, that's close enough. That's 2. I'm not sure why 1 didn't work there for a second. I guess that makes sense. I guess because the reason why, because standard deviation of 1 point isn't really a value, it's just 0, right? So basically know that our standard deviation is changing over here. So like you can kind of see like how it changes over time. But anyway, I'm going to go back to 6. Okay, so you can kind of see it kind of smooth out. So if I looked at just the red here, it looks a lot smoother. But note that also that this average part, it's going to do worse for exponential trends over time. You can see it underperforms like what you would think like as a kind of like the trend between here. Like if I drew a line that kind of like would kind of explain this part. And the reason why is because exponential trends are getting bigger and bigger and bigger. So what happens is that those lower values kind of bring down the average, right? So if I averaged over these 6 points, it's going to really be affected by this small point. So it's always going to kind of underperform versus like over here, it looks more or less linear. So you can kind of see it more or less as an average here. If I add more points, let's say I do like something like a rolling mean of like 10, what do we expect the red line to look like? Is it going to get more curvy, less curvy, all that stuff?
It should get smoother.
Yeah, it should get smoother, right? Yeah. Well, you kind of hope so, right? Because like basically you have less kind of fluctuation because you're kind of including the things in the past. So there's less for it to move around. So if I do this now, you can see it definitely gets a lot smoother. It becomes almost like line-like. Also note that I'm also moving this point further to the right because obviously I can't average in the past 10. There's ways you can kind of make it move. So it's like only looking at the average beforehand. But in general, you kind of like do this a rolling average and not include points that are to the left of this. Okay, so you can kind of imagine like, what if I do an at window of 1? What would that look like for this red line?
Would it be a lot more similar to the blue line?
Yeah, a lot more similar. So in this case, we're averaging over 1 point, which an average of, if I say the average of 10 is, if I have just 1.10, so the average of that is just 10. So essentially it is that red line here. So yeah, and you can see like if I had started off with something like 3, you can see it's pretty close. And then 2, obviously, to the previous points here, it's still pretty close in there. So you can see here, it still smooths it out. So you can also talk about this as smoothing. Okay, cool. All right, and then our next part is our Dickey-Fuller test. So our Dickey-Fuller test is kind of a nice little statistical test that says with statistical, there you go, if our test is, or sorry, if our time series is stationary. So the idea here is that if you get a significant p-value, we would say that the time series is not stationary. So our null hypothesis is that this time series is stationary and just using this part. So this is kind of a nice way for, instead of me saying it looks stationary, actually using some hypothesis testing and say, oh, we can actually say with a certain p-value, this is statistically significant, or is statistically significant, how do I say this? Oh man, brain's going. Is it stationary? Oh man, anyone want to help me out with saying this?
It's statistically significantly stationary?
Yeah, I think that's the best way to phrase that. Like, it sounds awkward, right? But the idea here is that we're basically saying, oh, it's stationary to a p-value of this, which means it's statistically significant. So I don't know. There's probably better ways to phrase this and stuff, but the idea is the same way. So what is nice is that stats models does have this Dickey-Fuller test built in. So this is the add Fuller here. And we can basically do this part, and this will pull out basically our test statistic, our p-value, and also say like, you know, how many lags we use. So this is very similar to the curriculum. So you can see here for our p-value, let's see, I have print test. Oh, print test. So our p-value is, where's our p-value?
You have to print df output, not df test.
Thank you. There we go. Much better. Thank you, Andy. Yes, this is just basically talking about, this is why, I'll be honest, I don't like stats models as much because they don't like using OOP, which makes it really difficult to be like, what exactly am I pulling out from here? Because it's just a tuple. But this makes a lot more sense here. Cool. And we can see here our p-value is 1.0, which means we cannot reject the null hypothesis, which means it's stationary, or at least it's statistically significant that it is stationary since we failed to reject the null hypothesis. So if this p-value is less than a certain value, we would say, oh, this data is not, this time series is not stationary. Make sense? Okay, cool. Any questions?
Wait, I'm confused. The null hypothesis for the Dickey-Fuller test is that it's not stationary or that it is stationary?
That it is stationary. I think that's why I wrote. Pass Victor, don't mess me up. Of course, I don't like this one. No, here. The null hypothesis is that there is a unit root with the alternative that there is no unit root. P-value is above critical size, and we can reject the null hypothesis. P-values are obtained to the regression surface. It's close to significant. True value should be judged. So I believe unit root. Yeah, it should be that the p-value, because let's see here. Let's check out this time series. What do I have right now? You let me plot predictive PLT. Yep. I got it backwards. So this should not be stationary. So, Pass Victor, why did you do this to me? Good catch, Jenny. Not stationary. So it should be saying that it's opposite. So this is saying that it is, sorry, we failed to reject the null hypothesis, which means it's not stationary. Cool. Thank you. Yeah, something seemed wrong about that too, but I'm glad you guys caught that. Good job. All right. Yeah, any questions on this then? Or at least, yeah.
What, so I noticed that the curriculum has us pull out those critical values, 1, 5, 10%. What does that mean? What do we do with that?
I believe this is, let's double check this. This is 1%, 5%, 10%. I want to say this is the test statistic right here. And this is saying a 5%, which is a point, like our alpha 0.05. This is the, this would be the value that we would need. Yeah.
Okay,
and so,
cool.
Yeah. So you can kind of imagine is that like, and that's our test statistic right here, right? So you can see our test statistic is not lower than these points right here, which means, or any of these points, that means it's not significant even at the 10% level.
Cool. Okay. Thanks.
Nice. Yeah. Oh, and here it is too. Critical value, 1%, 5%, 10%. Yeah. When we say critical value, that's for the alpha, right? And 1% meaning 0.01. Cool. All right. Awesome. Cool. Oh, yeah. Real quick, kind of like general hypothesis testing, right? So I can make it clear, is that we can usually talk about the p-value. Saying like, if your p-value is below 0.05 or, 0.1, we can go off of this. So you could, for example, completely ignore this guy and just go off of this thing. But an equivalent thing you can do with any statistical test is if you look at your test statistic, which is this guy, and your critical value, and your critical value, remember, like your t critical value is going to be it's not necessarily between 0 and 1, unless you're doing like a z-test. And so this basically can be compared directly with this guy. And this has come from the fact, it's like, okay, if we were to say a 1% or 0.01, right, we would need a critical value that's at least this large, or sorry, at least this small. And so you can either compare the test statistic and the critical value, or you can look at just the p-value. So just in the p-value is kind of taken these two parts into consideration, essentially what your test is, and then what's the critical, or what's the test statistic, and you converts it over into essentially something equivalent to like a z score, and then compared. So yeah, note that for the most part, though, I think people use p-value because it's kind of standard. We kind of like, oh, you don't need to know like this value means nothing to me with by itself. It's like I don't know like what the Dickey Fuller distribution is, but I can know what a p-value is regardless of tests. Cool. All right. Awesome. I'm glad, Jenny, thank you for pointing that out because I'm so glad. That's really, I feel bad that this was not there. Yeah.
So it's fine.
Perfect. All right. Cool. So next time then, we will talk about removing trends and time series decomposition, which will then lead us into a little bit of modeling and stuff. So this will basically, we'll start removing these trends. And the reason why we've removed these trends is really because we're trying to get to a stationary time series. And basically the stationary is saying, hey, all the rest of it is essentially like, I call it noise, but maybe that's not the best word for it, but other things that are affecting the value in the time series besides just the time. And essentially that's what these trends are. They're purely based on time. That it's going exponential, it's going upwards, it's going seasonality, it's periodicity, right? So that's kind of what we're doing, trying to remove those trends to see what is left over. Okay, cool. All right, so I'll go ahead and stop recording here unless you guys have questions. Okay.